Hello everyone, we are going to take notes on 11.2 exponential functions. First, we need to define what an exponential function is. An exponential function takes the form y equals b to the x, where x, our variable, is found in the exponent position. Normally we see x down as a regular constant position, like where the b is, or where the y is located. But this time we see variable up in the form of an exponent. We have to be careful that b is positive. B is a positive real number. We have two different situations when we're graphing the exponential function. First, we will graph when b is greater than 1. Okay, so when b is greater than 1, we can look at an example, for instance, like y equals 2 to the x. 2 would be our b value, and it is greater than 1. Okay, so to graph that, we're going to plug some values in. So we'll make a little table. So we have our little x and y. And we'll plug in some values like -2, -1, 0, 1, and 2. Okay, so the easiest one to plug in actually is 0. If we put 0 in, we would end up with 2 to the 0. And hopefully we remember from our laws of exponents that anything to the 0 is 1. So we're plotting the point 0, 1. We plug in 1, we get 2 to the 1, or 2. So we plot the point 1, 2. We plug in 2, we get 2 squared, which is 4. Okay, if we go in the other direction, we plug in -1. That'd be 2 to the -1. Well, laws of exponents says we can move that to the bottom, so that becomes 1/2. So -1 is a half. That's a little bit too far. And plotting the last point, if we put in 2 to the -2, 2 to the -2 would be 1 over 2 squared, which is 1/4. So that's going to be really close to the x-axis. Alright, the other thing we have to be careful with is all exponentials have a horizontal asymptote at y equals 0. Okay, at y equals 0. Alright, so if we connect this graph up, we get a nice smooth curve that grows exponentially. And remember, as it comes out to get close to that horizontal asymptote, it will get closer and closer and closer, but never actually touch the horizontal asymptote. Okay, so we call this the growth. This is exponential growth. This is what you'd want your money to do. Okay, you want this to grow exponentially. There's also a bad side to this. Bacteria, for instance, grows exponentially. So it's probably why you get sick so quickly, because once you get a bacteria in your system, it will grow extremely quickly. All right, let's take a look at the next type of exponential graph, and that is when b is between 0 and 1. So let's take a look at an example of y equals, let's say, 1/2 to the x. Alright, so again, we're just going to make a little table here, x and y, and we'll plug in some values like -2, -1, 0, 1, and 2. Again, I like to start with 0. So if I put 1/2 to the 0, okay, again, we're going to get 1. Anything raised to the 0 is 1. Okay, plugging in 1, we get 1/2. And if we plug in 2, we get 1/4. So you can see it's getting smaller. Again, we do have a horizontal asymptote. A little trouble drawing a point there. Alright, so we do have a horizontal asymptote again at y equals 0. So remember, as we're going out this time, looks like to the right, we will be approaching that horizontal asymptote of y equals 0. Going in the other direction, we plug in -1 and -2. Well, if I take 1/2 to the -1, what that means is we're going to flip that over. So when we flip that over, it becomes 2. So -1, 2. And if we flip, if we take 1/2 to the -2, that would be 1/4. I'm sorry, flipping that over would be 2 squared, or 4. And connecting that up, we see a very similar curve that we saw earlier, but just in the opposite direction. Looks like we have a reflection actually across the y-axis. Okay, if the exponential graph goes down from left to right, we call that exponential decay. Okay, exponential decay would occur in, for instance, in chemistry with radioactive substances. A really good one, actually. A good example is Newton's law of cooling. If you take a boiling water, put it into a cup, and measure its temperature over time, it actually will decay. The temperature will decay. It'll drop very quickly, and then very slowly smooth out to what the room temperature is. All right, so let's move on to a couple examples here. So we're going to graph 2 examples here. Y equals 4 to the x. We'll do that in blue. And y equals 4 to the x plus 2. We'll do that in red. Okay, so let's get the graph here. We're going to take the same approach as we did last time. So we're going to be plugging in 0, 1, 2, -1, and -2. Okay, so for the blue graph, make a little table here, x and y. So again, -2, -1, 0, 1, and 2. And for the red graph, make a little table also. X and y, same thing, -2, -1, 0, 1, and 2. Alright, so we'll start with the blue graph. If we plug in 0 again, every time you put 0 in for that exponent, anything to the 0 becomes 1. So, okay, so 0, 1. If we plug in 1, we end up with a 4. If we put a 2 in, we would get 16. Now it's growing very quickly. Actually, I'm going to have a difficult time drawing that, so I'm just going to not draw that one. And -1, we would have 1/4. So that gets small very quickly. And looks like we're going to have the same problem with -2. If I took 1/4, okay, to the -2, we'd end up flipping that fraction and squaring it, which would be 1/16. Also going to be very difficult to show on this graph. So I'm just going to go ahead and put in my horizontal asymptote at y equals 0 and just leave it there. Go ahead and draw this off this 3 points we have here. Okay, so that would be a growth. Okay, it looks like a definite exponential growth. growing a little bit more quickly than 2 to the x. All right, let's look at what happens when you take 4 to the x plus 2. If you can remember back a while ago, we studied transformations. In transformations, we had 2 on the end of a function. That tells us that we need to take it up 2. So there's a vertical shift up 2. So the first thing I would do is I'd take my horizontal asymptote, that's it, at y equals 0, and I'd move it up to y equals 2. Everything gets to move up 2. So my point that is at, actually let me make that different color. Let me make that horizontal asymptote. Let's make that green. Since I'll be putting the graph in red. Okay, so again, we have a horizontal asymptote at y equals 2. And all of the other points are going to move up 2 as well. So 0, 1 becomes 0, 3. Negative 1, 1/4 becomes negative 1, 2 1/4. And 1, 4 becomes 1, 6. Okay, so here's our second graph. Again, it's pretty much the exact same graph, just shifted up 2. So both of these are growths. Growth, exponential growth. I forgot to fill out the chart over here. So this is 0, 3, 1, 6, and negative 1, 2 1/4. And we didn't graph the other 2. All right, let's take a look at another example. Okay, very similar question. We're going to graph y equals 1/5 to the x. Again, let's go ahead and do that in blue. And then we're going to graph y equals 6 times 1/5 to the x. And we'll do that in red. So we should already be thinking about what is that 6 going to be doing to our original graph, the first one, the blue. What type of transformation will we be seeing? Okay, so I think 0, 1, and negative 1 is going to be sufficient to graph these. So we'll make just a small chart here. Negative 1, 0, and 1. Also for the red. Negative 1, 0, and 1. Okay, we'll plot some numbers here. Again, anything to the 0 is 1. So again, we're going to have zero, 1 plotted. And I put in 1, I get 1/5. All right, so this is looking like a decay problem. And if I put in negative 1, I get 5. Okay, if we connect those up, definitely looking like a decay. Okay, and we'll be approaching that, put it in green, horizontal asymptote at y equals 0. Alright, so this one might be easier to think about by just plugging in numbers and actually working it out. So what's the 6 do? Well, let's plug it in. Let's see. So if we put 0 in for x, what we end up with is we end up getting 6 times 1, or 6. So what was at 0, 1 is now at 0, 6. So it looks like to me what the 6 does is causing the value to be 6 times what it used to be. If I plug in 1, okay, so put a 1 in up here. Maybe 6 times 1/5, or 6/5, or 1.2. Okay, so what was at 1/5 is now at 1.2, which is 6 times it. So this last one's going to be way up there, because if we put a -1 in, that would become a 5. So 6 times 5 ends up being 30. 30. We go all the way up to 30. I don't know if I have enough room for that. Let's see here. We're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're going to cheat here. We're going to say break. And we're just going to say that's 30. All right, that's not very accurate. And you're going to get a much better graph if you put this on graph paper. But since I'm kind of running out of room here, we're just going to say there's a little break in the graph, and it's going to go all the way up to 30. So the 6 simply causes our exponential decay to become 6 times larger. So it's a vertical stretch of 6. All right. Moving on. All right, we have some notes that we have to deal with. The exponential comes in different forms. Now, this exponential growth or decay formula is for population growth. Okay, a certain amount of growth over a certain amount of time. So what we have here is we have this equation of n equals n sub 0, or original number, n sub 0, n original, times 1 plus r is the rate, to the t. T is the time. So where n is the final amount, n sub 0 is the initial amount, or original amount, r is the rate of growth or decay per time period. Now that time period could be any time period. So it could be so many per day, per hour, per week, per month. The key to these type of problems is that the time has to match the amount per time period. So if it's going to double every week, and I want to know how long it's going to be, or how many there's going to be, say like in 3 years, we're going to have to convert those years to weeks. Okay, so they have to match. The times must match. So if we're going to do weeks, it has to be both in weeks. Or if we're going to do days, they have to both be in days, and so forth. All right, so let's put this formula into action. Okay, so here we have a colony of 500 bees is increasing at a rate of 14% per week. Okay, there's our answer. Okay, everything's going to have to be in weeks. Okay, if we want to use that rate of 14%. What is the expected population in 2 years? So immediately, I'm already looking at how many weeks are there in a year. If my memory is correct, I believe there's 52 weeks in a year. So we're going to have to find out the t-value. Instead of 2 years, we're going to have 104 weeks. Okay, which should be the equivalent of 2 years. 52 weeks doubled. Okay. All right. So let's take our equation. N equals n sub 0, 1 plus r to the t. We're just going to plug in everything that we know. What is the expected population to be? So that's our final number. So that's not going to be known yet. What is our original number? N sub 0. Looks like we have 500 killer bees. 1 plus our rate. Now our rate is 14%. We can't put a percent into the problem, so we're going to write that as a decimal, 0.14. And again, you cannot put 2 in for time. Okay, we have to convert that to weeks, so we're going to raise that to 104. Wow, that is going to be a very, very large number. Alright, so let me get out the TI-83 calculator here so we can calculate this. Alright, so 500 times 1 plus 0.14 to the 104. Okay. Oops. Calculator went away. 414070741. 41407. See if I can get that to stay on the screen for us. Okay, I think I got it to stay on the screen. 414. There we go. 414070774. Let's say 1 B's. Wow, that is 414 million B's from 500. That is a very, very, very large amount of bees. But if you think about it, is it possible that this actually occurs? Well, you'd have to go in, you'd have to do some research on the killer bees. I have no idea how long they live. If they live more than 2 years, untouched, somewhere in the world, yeah, this could happen, which is very scary because that is a ton of bees that would be after us. All right, that's moving on. Okay, compound interest. Very, very powerful concept. We have A equals P times 1 plus R over N to the NT. Okay, so that's what we want to focus on. Slightly different letters than what we used last time. Notice that we had to use A and P simply because we now have an N involved in the equation. Okay, so this is mostly for banking use, money use. P we call the principal or initial amount. Banks love to call the initial amount of money a principal amount. A is the final amount. R is the annual interest rate, specifically annual. Okay, so we're saying that's what it has to be down to. The banks always use an annual interest rate. N is the number of times interest being paid or compounded each year. So banks have a tendency not to just pay out interest one time a year. They actually usually go to daily. That's often the time that they use. I have seen quarterly, monthly, but mostly daily. T is the number of years that our money will be invested. Okay, so again, we're saying annual rate and number of years. So we're sticking with the idea that they have to be the same, but we're saying that it is going to be years instead of it possibly being weeks or months or something else when the last time we did it, the population problem. Okay, so here's our example. So if we're investing $2,000 compounded daily, okay, as banks usually do daily, and the annual rate of 5%, which is a phenomenal percent right now. Most of you, if you have a banking account, say like a savings account, will probably be lucky if you get 0.5%, if you're lucky. Actually, that's probably way too. You might get like 0.05%. That's very, very low right now, or 0.1%. How much will you have in 7 years? So if things go well, if interest rates go back up, the rates of our savings accounts will as well, and we'll be making more money. So if we ever see 5%, you'll know what we're dealing with here. So let's write down the equation. A equals P times 1 plus R over N to the NT. All right, let's plug in what we know. How much will we have in 7 years? That's our final amount. We don't know yet. Principal amount, we are investing $2,000. 1 plus our rate is 5%. Again, we're going to put that into a decimal. Okay, so 5% in the form of a decimal is 0.05. Right? Over n, number of times. So, we use 360 or do we use 365? There's not much of a difference. We're going to go ahead and just use 365. To the nt, so 365 times the number of years, in this case 7. So it's going to be a very large exponent. Alright, type this all in. Alright, so 2,000 times 1 plus. Now unfortunately I do not have the vertical fraction with this version, so I'm going to have to use parentheses. Okay, so 0.05 divided by 365. We'll need another parenthesis to the parenthesis again, 365. Oops. Times 7. Okay, so you can see that's our formula. So we're getting 2,838.07. Pretty cool if you were able to put $2,000 in a bank, don't touch it for 7 years, 5% interest. The bank's actually give you back $838.07 for pretty much doing nothing except for just breathing. So, all right, that's it. That's all I have for you today, and good luck on your homework.